Today we discuss complex fractions, and the title might sound like it's going to be a barn burner, but they're really not that complex. The idea behind complex fractions is basically it's defined as a fraction, like 3/2, over another fraction, 5/7, which really means, in essence, that it's the same as 3/2 divided by 5/7, which isn't really hard at all right? And we know that we can solve that by taking 3/2 and multiplying by 7/5, which is 21 over 10. Now there's another way to go about doing this. The way I kind of like to do it is if I have 3/2, I mean this isn't hard, but as the problems get tougher, I think this might be a better way to go. If I were to take and multiply by any form of 1, I wouldn't change the value of this answer. So if I look at the denominator here and the denominator here and say, okay, well, that common denominator would be 14, and I multiply the top and the bottom by 14, notice this goes to a 7, all right, 14 over 2, which is 21, and this is 14 over 7, which is a 2, and 5 times 2 is 10. A lot less work. So again, my idea is look at the denominator of both the numerator and the denominator, multiply by that form of 1, and then get the answer, thus clearing basically all of your fractions. So I'm going to apply that to this problem. So I have a denominator, in this case, of 4, 8, and 12. And if I want to find the LCD of all of that, then I'm going to say, okay, well, that's probably not going to be 12 because 8 doesn't go into 12, so I'm going to go with 24. Multiply by 24 over 24, and really this is 24 over 1, if you will, and 24 over 1, if that gets you confused. All right, so then when I'm distributing, I multiply the numerator by the numerator and the denominator by the denominator. Thus, I get the following. I get 24 over 4, which is 6. So 3 times 6 is what I have there. And then I have 24 over 8, which is 3. So that's subtracted by 1 times 3 all over. And I'm doing this, slower to show you guys how to get the answer. 24 over 1 is 24 times 2. So I've got 2 times 24. And then here I have 24 over 12, which is 2. And that's basically 1 times 2. All right, so then I clean this up a little bit. I've got 18 minus 3 over 48 plus 2, or 15 over 50. All right. And after doing that, I figure, okay, well, 5 goes into those, 3 times here, 10 times here, and I'm done. So now we throw variables into the mix. Again, find the common denominator of both the numerator and the denominator. I'll just put a 1 here. So I've got c squared as a denominator here, and then c and c squared here. The LCD is going to be c squared over c squared. Again, I'll take and distribute that through to both the numerator and the denominator, giving me a 9c squared in the first multiplication and a 1 in the second multiplication. Going over here, I get rid of one of the c's on the reduction, so I have 3c, and then I have the c squareds going, so that's minus 1. Now I look at this and I say, hey, I got a difference of 2 squares, so I will factor that and do 3c minus 1 and 3c plus 1 over 3c minus 1. Note, all multiplication and division, these are like factors, they reduce. My answer, 3c plus 1. This problem always confuses people because what they typically want to do is they want to take and move the x squared down and the x up, y squared down, y up. But the problem is that's not a single multiplication and division. You've got this addition which makes these things inseparable. So this is really equivalent to 1 over x squared and 1 over y squared over 1 over x and 1 over y. Common denominator of both the numerator and denominator is going to be x squared y squared. And I'll distribute that to both the numerator and denominator. In so doing, I'm going to get the x squareds to reduce, so that's y squared plus x squared, which will not factor. And then over here, I'm going to get x, y squared. And here I will have x squared y. Now you can, like I always do, look to see if anything factors. The numerator does not, as we said before. So unless I get y squared plus x squared, this is not going to reduce. And I've got a y squared and an x squared over here, so let's just see what happens. I pull out an x because that's in common. I pull out a y and that's in common. And I'm left with a y plus an x. Again, don't be fooled into reducing these because this would have to factor into a factor of y plus x to be able to reduce. So that's going to be my answer. Now we're going from basically monomials in the denominators to binomials. And in this case, it looks like I've got a 3x plus 1 on one term and a 1 minus 3x on another term. I'm not a big fan. I, again, like representing these where I have my leading term, which would be the highest degree term, as a positive number. So I'm going to rewrite this right off the bat and say this is 3x plus 5 over 3x plus 1. And this is, again, it's kind of a pet peeve of mine. You don't have to do it this way, but I find I make many fewer mistakes when I do it this way. So this is 3 over 1 plus, actually that's not going to be a plus. Notice when I pull a negative out, it will make the second term a subtraction of 3x. And since I've pulled a negative out of here, I get a 3x minus 1. So now I look and I say, all right, well, I've got an LCD top and bottom of 3x plus 1 and 3x minus 1. I'm going to multiply by that form of 1 to both terms. Likely I'm going to have some foiling to do. So when I multiply over here, the 3x plus 1 goes. I'm just going to write this out for right now as 3x plus 5 and a multiplication of 3x minus 1 plus, these are a difference of squares, so that's 2 times 9x squared minus 1 over. Again, I've got a 3 times difference of squares, 9x squared minus 1 minus the 3x minus 1's go, 3x times 3x plus 1. All right, now the foiling comes in. There's my 9x squared. Negative 3x, positive 15 gives me a positive 12x minus 5 plus 18x squared minus 2. That's all over 27x squared minus 3 minus 9x squared minus 3x. Clean it up. It's looking to be 27x squared plus 12x minus 7. I don't know if that's going to factor. Highly doubt it, but I can check. And that's 27x squared. Whoops, I lied. It's not. That's going to be 27 minus 9 is 18x squared minus 3x minus 3. Okay, that I definitely know factors. So we're going to have to take a look at this. Now you can factor this top any way you want. I'm going to just go ahead and try and guess and check that. And I'm going to just shoot the breeze and give this a shot. I know, let's see. I know this. I know I've got to have a 7 and a 1. That's for darn sure, because no other way am I going to get that 7 in my final multiplication. And then I've got to look at what makes it 27. Well, I can go 27 and 1, which I'm highly doubting is going to work. So I'm going to go 3 and 9. And I probably don't want to multiply that 9 to that 7 because then I get a big middle term. So I'm going to put, I said a 9, right? 9x here, 3x here. I need 12 to be positive. So I'm going to make the bigger multiplication positive and this negative. Let's just see. There's 27. 21 minus 9 is, hey, it works. What do you know? All right. And then here I'm going to pull out a 3. And let's just do this on the side over here in green. I'll have a 6x squared minus x minus 1. There's only one way to get 1, so I put a 1 and 1. Going to need a positive and a negative. And my bigger term is going to be negative. I could go 6 and 1, but that's not going to work. So I'll go 3 and 2, and I said my biggest multiplication's got to be negative. So 3, 2, there's 3 and negative 3 and 2 is negative 1, and there's my 6, and there's my, hey, this works too. What do you know? So this is going to be 3x plus 1 and 2x minus 1, and I'm so close yet so far away. These don't go into each other because they're not common factors. So this, in essence, was my answer. I could represent it as this. And like I said, I always want to go back and factor just to make sure nothing reduces. And it didn't in this case, but we did a little factoring on the way, so that was good. All right, continuing. Fairly straightforward problem. W plus 2 on top, W minus 2 on the bottom, or at least it appears to be straightforward. Multiply by W plus 2, W minus 2 to the numerator, and W plus 2 and W minus 2 to the denominator. This is not going to be pretty. So this is going W times W squared minus 4. I just multiplied these two together. The W plus 2 goes, and I'm left with a W minus 2 over, I don't like that cube that looks like it's going to show up. It's a W squared times W plus 2 added to W squared minus 4. And I'm still not happy about this because I'm going to have a W cubed, and I'm going to have a W cubed down here. So I'm not happy at all, really. I'm going to write this a different way. I think this was the right way to do the problem. So what I think I'll do is I will take, and instead of writing it as the product of W plus 2 and W minus 2, yeah, this will be better. I've got W plus 2, W minus 2 plus W minus 2 over, and then I'm going to have a W squared W plus 2 plus W plus 2 W minus 2. Okay, you're going to hate me for doing this because I'm going to finish the problem this way, and then I'm going to do it another way. You'll notice in this case I have a GCF. All right. My GCF in this case is the W minus 2's. Likewise on the bottom, I also have a GCF of W plus 2. I'll circle those because it's a different GCF. So in the numerator, I'm going to factor out a W minus 2. And you'll note, I'm going to put a bracket and say what's left then are these two terms, which is W squared plus 2W. And then what's left over here is a 1. Kind of like that because I notice W squared plus 2W plus 1 is factorable. Now over on this side I've got a W minus 2, and when I pull that out, oops, I lied, I have a W plus 2, sorry. When I pull that out, I'm left with W squared plus W minus 2. Okay, so this is great because this goes to W minus 2, And then I have w plus 1 quantity squared over w plus 2 and w plus 2 and w minus 1. Well, it did work out great. However, we notice that in this case, nothing's going to reduce because I have no common terms. So I just have w minus 2 and the quantity of w plus 1 squared over w plus 2 squared and w minus 1. Now, all that extra work just to get something that doesn't reduce in the end. This happens. So I'm going to show you a way to maybe avoid some of that work. So instead of finding the common denominator of both the numerator and denominator, which I would have never known, but again, I saw something about halfway through the problem because I've been doing this forever that might help me do it quicker. So what I'm going to do instead, I'm just going to do the numerator by itself, then the denominator by itself, and then multiply by the reciprocal. Kind of the first way we did the problem with the two fractions. So I see that I have a common denominator of w plus 2. So this goes to a w times w plus 2 plus 1 all over an LCD of w plus 2. On the bottom, I know I have an LCD of w minus 2. So this is w squared plus w minus 2 over w minus 2. Holy cow, this is looking easier already. So then I've got w squared plus 2w plus 1 over w plus 2. Notice what I'm going to do now. I'm going to multiply by the reciprocal of this guy. This is a w minus 2 over w squared plus w minus 2. Hey, notice anything? Looks very, very similar to what we had right up in this step over here. There it is. So really, I'm pretty much done. Again, w plus 1 quantity squared times w minus 2. This goes to a w plus 2 times w plus 2, w minus 1. And you can simplify that. I'll get the same two answers. So it just becomes a case of doing them enough to see which way you're comfortable with. I can get out of a jam pretty much any way. You may or may not be able to. So once you start recognizing where you might have problems, and the problems basically come when you start looking at possible cubes in your problem, then you want to try to avoid that so it doesn't happen again. Let's do one more. Now this is a little different in that in my common denominator, I've got a y, a x plus y, and an x minus y. When I'm looking at three possible terms, I'm likely going to do the top separately from the bottom, just like we did in the last problem. So let's approach it that way this time. And it might just work out pretty easily with no cubes. So in this problem, I have a common denominator of y and x plus y in my denominator. Therefore, this term needs a multiplication of an x plus y. And this term needs a multiplication of a y. Over. This has a common denominator of y and x minus y. So my first term is going to need a multiplication of an x minus y. And my second term is going to need a multiplication of a y. So now I'm going to clean things up a little bit. I have x squared plus xy minus xy plus y squared over my y and my x plus y. Now watch what I'm going to do. I'm going to multiply by the reciprocal, so I have a y and an x minus a y over x squared minus xy minus xy minus y squared. Okay, I'm going to have to clean this up a little bit. Middle terms go, x squared plus y squared. We know that doesn't factor. We've seen that enough already. What I'm going to do is I'm going to get rid of these y's right off the bat because they reduce with each other. So I have an x plus y in the denominator here, multiplied by, this is an x minus y, over x squared minus 2xy minus y squared, which I don't think is going to factor. So that's pretty much it. Done. And I think that would have been a lot more difficult had we taken a common denominator of y, x plus y, and x minus y, and run through it that way. But you can try for yourself if you want. Otherwise, we're done for the day, and we'll see you tomorrow.